All right, so we're going to be sketching polynomials, and we're going to talk about what we call end behavior. What is the arrows of the graph doing? And that's how we're going to decide which direction to draw the polynomial in. But we have to know certain vocabulary terms to do that. And these vocabulary terms also become important in what we're going to do next week. So the leading coefficient is the coefficient on the term that has the highest exponent. Okay, the degree of a polynomial is the highest exponent. If there's more than one variable, like x and y, then we add the exponents to get the degree. That's not used that often. But it's one of those easy things that if you remember, oh, degree is highest exponent, add them if there's more than one within one term. It could help you on like standardized tests. And the constant term is the term without the variable. Okay, so here's an example. We have 4x to the fifth plus 3x to the fourth minus 2x cubed plus 8x squared minus 17x minus 30. So this is a polynomial. Okay. The leading coefficient, what would you say the leading coefficient is? 4. The leading coefficient is the number in front on the term that has the highest exponent. What would you say the degree is? The degree is the highest exponent. 5. So my degree is 5. And my constant, what would my constant be? Negative 30. The constant is the number without a variable. Okay? So these terms are important. They're how we identify certain parts of the polynomial. Now, polynomials have names very similar to our polygons. A first degree polynomial usually looks like mx plus b. Those are linear. Positive line goes up from right to left. A negative line goes down from right to left. Remember, or I'm sorry, left to right. We read graphs the way we read books, left to right. The second degree is called a quadratic. That's what we worked on all through chapter 2 and 3, quadratics. Those are parabolas. The positive parabola opens up. The negative parabola opens down. Third degree is called cubic. Now you're going to see that all the odd degrees generally look like the linear equation, and our arrows are in opposite directions. And the degree determines how many directions the graph goes in. If we look at the linear, it's in one direction. The quadratic is down and then up, so that's 2 directions. The cubic has 3 directions. The positive goes up, up, and the negative goes down, up, down. The fourth degree is called quartic. And that looks like a parabola, but it goes down, up, so more like a W. And the negative one goes up, down, kind of like an M. Fifth degree is called quintic. Sixth degree, and it goes up, down, up. But sixth degree is called sectic. Seventh degree is septic. Eighth is octic, like octagon, right? 9 is nonic. The nine-sided polygon was called a nonagon. And 10th degree is dectic. A 10-sided polygon is a decagon. You don't need to memorize any of these. It's just kind of like, oh yeah, I kind of feel like I heard that before, you know? When we look at end behavior, we look at the coefficient, the leading coefficient, and really end behavior is the arrows. What direction are the arrows going in? We'll look at some more formal notation later. And then we look at the degree, whether it's even or odd. Now, like I said, all the odd polynomials have similar arrows, end behavior, to the linear equation, the line. Lines, the arrows are in opposite directions, right? The ending arrow is positive on the positive linear equation. The arrows are again opposite, but the ending arrow is negative when it's negative. And the evens, so odds, odd degree, the even degrees start like parabolas. We're in the same direction and positive, both negative. So it's like this. Does the graph start in the negatives and go to the positives? It start in the positive and go to the negative. These are odds. The odds are opposite directions. My right hand, the right side, always ends whether it's positive or negative. Okay, the even's always the same. Okay, my evens are the same, so if it's positive, they're both going up, and if it's negative, they're both going down. Okay. So, I made this little table. We have this table. If the leading coefficient is positive or negative, and the degree is odd or even. We're just really interested in what the arrows are doing. Okay, we'll talk about, like I said, formal way of writing it later. But if it's positive and odd, my left arrow points down and my right arrow points up. Now, odd means it could do lots of things in the middle. It could change direction 5 times if it's 5th degree. So that's why we're just drawing the 2 arrows, right? The left arrow and the right arrow. Which direction do they go? If it's odd negative, my left arrow points up and my right arrow points down. If it's even positive, both arrows point up, and even negative, both arrows point down. To sketch, given the factored form, we don't really want to sketch the graph if it's multiplied out like this. That's not fun. You have to actually plug in a bunch of numbers, and that's a lot of polynomial to plug numbers in. So we really only look mainly at, can we graph it if it's factored? Okay? So it's a little different because you don't have it multiplied out to determine what the leading coefficient is and what the exponent is. But here, my leading coefficient, I'll abbreviate LC, would be any number in front of the parentheses. Okay? In this case, is my leading coefficient positive or negative? It's positive. Okay? And now, how do I determine the degree? Well, I think about if I multiplied this out, what would my exponent be? I have x times x times x. What would that be? To the third power, right? So it's odd because x times x times x is x cubed. Yeah. And then we have to find our zeros. Where does it cross the x-axis? It's already factored. We can find the zeros from this, right? X is what? What do I get from the first parentheses? Positive 3. What do I get from the second parentheses? Negative 1. What do I get from the third parenthesis? Negative 5. So we're going to put those points on our x-axis. We are not going to put numbers on the y-axis. This is just a sketch. Okay? So we're not going to worry about how high any of our points go on the y-axis. So negative 1, negative 2, negative 3, 2, 3, 4, 5. Put these in blue, sorry. And then 1, 2, 3. Okay. Now, based on our end behavior, positive, odd, show me with your hands what the graph should look like. Positive, odd. Yeah, good. So, sorry if you're listening to the video, you don't get that visual. So that means I'm going to start negative here, and it's going to end positive, right? If you think about how you put your hands out, the lower arrow is pointing down on the left, and then the right arrow is up. Now I just need to connect the dots. But not really connecting them, I'm going to go through them. Okay? So we know that the graph goes through the x-axis at our zeros. So my graph is going to go through the first one. It has to turn around to go through the second one, and then it turns around it again and goes through the third. And I didn't connect my arrow, but that's okay. And that's my graph, my sketch. I'm not really concerned with how high or low we go. If we really wanted to be accurate, we could plug in some numbers in between here and get that. But that's not necessary. This gives us a really good picture of the parabola. Or sorry, the polynomial. Okay. Questions? I could have so many arrows if I use my hand. Okay, let's look at the next example. F of x is negative x plus 1 times x minus 4 times x plus 2 times x minus 2. So what, is it positive or negative? It's negative. Is it even or is it odd? It's even. Why? Yeah, we have 4 x's, right? X times x times x times x is x to the 4th. Okay? And these are what we call single roots. The 0 only occurs once, so the graph passes through it. Okay? So what are my zeros? Negative 1. Positive 4, right? X minus 4 gives us a 0, it's positive 4. X plus 2 gives us negative 2. X minus 2 gives us positive 2. So and negative 1 and negative 2. So we put those on there. Show me with your hands. It's negative even. Negative even. Both down, right? So both arrows are down. And then we'll just pass through my points. Okay? Again, not real concerned with how high or low you go in between those zeros. The further apart they are, the lower it's going to go, or higher, lower or higher, depending which direction. Okay? Questions? Okay, so what if they're not all single roots? What if some of the factors are squared or even cubed? We're going to get to that next. Okay. One thing we do know is that a fifth degree polynomial should have five solutions. Some of them might be imaginary. Okay. Some of them might be double roots. Some of them might be triple roots. But there's 5 solutions to a fifth degree polynomial. So here we have negative 3 times x plus 4 times x minus 2 squared. Okay. We know that that x minus 2 squared means it's there twice, right? X minus 2 times x minus 2. So that's what we call a double root. And the word root and 0 and x-intercept all mean the same thing, where the graph crosses the x-axis. Double roots do special things. It's like it wants to go through the point twice, but it really can't. So what it does is it creates its own little mini parabola within the graph, because x squared is a parabola. So let's look at this. Is this even or odd? It's odd because x squared times x, right? Is it positive or negative? Negative. Okay. What are my zeros? Negative 4 and positive 2. So what does odd negative look like? Show me with your hands. What do odd negative look like? Right. So my graph is going to start up here and end down here, right? It's going to start in the positives and end in the negatives. Now I'm going to go through my single root, which is negative 4. So I go through that one. But because this is a double root, it wants to go through it twice and it can't. So it bounces off of it, makes its own little mini parabola. And then it connects to my arrow, or it'll turn around and go through other points. Okay. So the double root makes a mini parabola. Or, I like to say it bounces off the axis. Yes? Okay. Now, I want to show you what x cubed looks like, because I think this will help this make more sense. The graph of x cubed looks like this. It goes up and it's, like I like to say, it kind of snakes through that point at 0, 0. Because that's its only 0. If you think about the way a snake moves on the ground, right? It's moving through there kind of like a snake. So when we have triple roots, then they look like this when they pass through it. This is called an inflection point because it goes from concave down to concave up. That's why it's called an inflection point. But I just wanted you to see that this is what x cubed looks like. So it kind of makes sense that when I have a cube root, it does the same thing. Okay? And like when I change this to x to the fourth, it kind of looks like a parabola that's a little flatter at the bottom. When I change it to x to the fifth, it looks a lot like the x cubed, doesn't it? It's just a little bit flatter in the middle. So the odd roots all end up doing the same thing to the graph. And the even roots all do the same thing as the x squared. So our x squared, our factors here that are squared, or fourth power or sixth power, all do this bouncing action. And when we have one that's cubed, like in this last example, it makes an inflection point like the x cubed graph does, okay? Or it snakes through it. Same if it was to the fifth power. It would look very similar. So this is called a triple root. And it makes that kind of motion through the point. I like to say it snakes through the axis. So technically I have 3 x's here. So that's x cubed times x. What do I get? Is x to the fourth, so it's even, right? And my leading coefficient, or my coefficient out here, is positive. So we have even positive, which is what? What does it look like? Yeah, both arrows are up. Okay, so my arrows are up. I have -5, right? X equals -5 and 3. So when it comes down through that -5, which is my triple root, it's really kind of a subtle little curve. And then it goes down and turns around, and it goes through my other zero. And then both my arrows end up. So triple roots and fifth roots are going to make that snaking motion. Second root, fourth roots, sixth roots will make the bouncing parabola action.